Welcome, everyone, to the ninth Igniting Research Passion series, hosted by the IEEE WIE Student Branch Affinity Group of the University of Jaffna, where today we will be focusing on the groundbreaking topic NLP pipelines for pediatric healthcare, which is all about using the facilities of natural language processing to efficiently sort through and better understand medical texts, such as doctor's notes, to help doctors, particularly pediatricians, when it comes to treating their patients. Our speaker for the topic today is Dr. Pavithra Rajendran, who is currently leading the NLP and computer vision workstream at Ghosh Drive, which is focused on adopting AI techniques and developing solutions for analyzing and extracting insights from unstructured clinical texts and images. She has around 8+ years of academic and commercial experience in translating academic knowledge and research to building appropriate end-to-end solutions, starting from proof of concept all the way to production. Dr. Pavithra has also prior experience using both traditional and deep learning-based NLP techniques for various client projects in both public and private sectors. She notably holds a master's in advanced computing, specializing in machine learning, data mining, and high-performance computing, and a PhD in computer science, specializing in natural language processing. Without a doubt, she's the perfect speaker to discuss the topic today. So without further delay, we hand over the session to you, madam.
Right. Thank you all, and thank you for inviting me. So to begin with, I'm Rajendran, so I'm a senior data scientist at Ghosh Drive, and today I'm going to be talking about how we build NLP pipelines for pediatric healthcare datasets. So in terms of today's agenda, so I'll provide a quick introduction about Ghosh, our drive unit, and I'll also provide some overview of some of the key topics within natural language processing, how do we translate research into practice, and some real-world example use cases that we work at Ghosh Drive. Right. So to introduce Great Ormond Street Hospital, it is the first English-speaking hospital that's been dedicated for children, and it is an acute specialist pediatric hospital with a mission to provide world-class care to children and young people with rare, complex, and difficult-to-treat conditions. And along with UCL, we are the first biomedical research center within the UK. So I work as part of the Drive unit, which is the data research, innovation, and virtual environments. And the Drive is, you could consider it as the innovation hub of the hospital. And some of our strategic goals include like driving digital connectivity and to make Ghosh become the go-to center for pediatric innovation and also deliver global impact, especially for our rare disease data and expertise. Right. So before I move on into the topic, I would like to thank all the individual contributors who helped with building our pipelines and also like kind of thank my entire team for their continued support. Right. So to begin with, let me start talking about large language models. So we know large language models has become the buzzword of today, and in fact, it has moved beyond just being a buzzword. So we know that there's been a rapid progression of generative AI, and literally every day we see like newer models being released. And but what exactly are these language models? So before we even talk about this, what is natural language processing? So natural language processing is a subtype of AI that enables machines to be able to interpret and understand the human language. And language models is not a new topic. So it has evolved from neural language models to training neural networks for producing pre-trained word embeddings. And a major breakthrough was with the introduction of the transformer network, which has in fact progressed with the emergence of a lot of variants of these pre-trained language models, and the current trend or the current focus being on training general purpose large language models with the availability of massive data and computational resources. To the next slide. Unfortunately, I think the animation is not working here, but anyways, so I wanted to talk about word embeddings, but before we even talk about that, to understand the context and meaning of word embeddings, let's consider like how do we represent words for a machine to learn. So unlike humans, a machine cannot understand the complexities and nuances of the language. So one of the simplest way is to represent them as a one hot vector or as a bag of words model. So if we take this example here, today is sunny. So for the word today, it could be represented in a mathematical vector representation as shown here. Even though this is kind of a good way of representing natural language text. There are some drawbacks to this. So one, as the number of words in a sentence or let's say a document expands, it produces sparse vectors. And the other one is it cannot capture the meaning of these words. So let's now consider the sentence on the right. So the cat sat. It should have been on the, like anyways, the cat sat on the, and let's say we would want to complete this fill in the blanks. As a human, we know that the highly likely word that could occur with the words cat and sat would be mat. And how did we do this is because we know which words can occur together frequently and produce a meaningful sentence. So similar to this, the core idea of these word embeddings or producing these word embeddings or mathematical vector representations is based on what is termed as distributional hypothesis. So what this hypothesis states is that words that occur in the same context could have similar meaning, and there are different algorithms developed, but two popular ones would be the word-to-vec algorithm and the glove. And while the purpose of these algorithms was to train these on a large corpus of unlabeled data to produce a dense vector representation for each words, the idea was to kind of capture the semantic similarity. But what research has found was while doing so, these vector representations are also able to capture some of the intrinsic properties such as the semantic and syntactic relationships. So as you can see in the diagram here. Yeah. So these algorithms are then trained on, as I said, trained on these huge corpus of data and to obtain what is termed as pre-trained word embeddings. And these pre-trained word embeddings have been really highly popular because they have been really successful in their use for downstream tasks, which um, you can kind of see this as a form of transfer learning. So for example, let's say we would want to train a sentiment classification model using some labeled data. And let's say we don't have enough of these data. So instead of training a model from scratch, trying to make it learn the specific data, these pre-trained word embeddings can be used for representing the features for the classifier. And studies have also shown that these word representations kind of capture different intrinsic properties when they are trained using different algorithms. So how do we know what is the best word representation for a particular task? Or in other words, can we leverage all the word embeddings and together? So this is where the meta embeddings prove to be useful. So the idea behind what is termed as meta embeddings is nothing but, so we know that we have all these pre-trained vectors having these rich vector representations. Can we embed them all together into a single vector space? So if you see the example here, let's say we have the word apple, and we have the vector representations from which we have obtained from training, let's say, n different algorithms. So a meta embedding function could be simply averaging these embeddings, or it could be even concatenating them to compute like a final embedding vector. And what research has shown that is by simply doing this, these meta embeddings can outperform all these individual vector representations. for any of your downstream tasks, or even simply just to, let's say we would want to find which words are similar together. So these vector representations are much better than some of the individual vector representations. Right. So the next topic is moving on. Let's look into pre-trained language models. So language modeling. So what is language modeling? It is the task of understanding the probability distribution over a sequence of words. Given a huge amount of data, are we able to understand this distribution? And with advancements in deep learning, so RNNs and LSTMs, they have been quite dominant in the field, but one of the major drawback of these neural models is they fail to capture long-term dependencies. So this is where I'm sure most of you might have seen this somewhere, is this attention is all you need paper. So this paper, I would say, kind of revolutionized the field of NLP. So this paper introduced the transformer architecture, as you can see on the left. So the key idea behind this architecture, like if we would want to simplify it, it is an encoder-decoder model. And the basic idea here is it heavily relies on what is termed as a self-attention mechanism. And what they do here is by stacking several of these attention layers, the model relies on attending to relevant parts of the sequence. And by doing so, it can also capture the long-term dependencies and knows which words to attend to in a particular text. And if you see the example here, let's take the word on the right, which is it. So we as human, we all know that it refers to the animal rather than the street. So this is the kind of uh, mechanism that this model is trying to do, is trying to attend to words that are quite relevant to this particular word. Right. So as I said, with the introduction of these transformer models, there's been like a lot of variants of these pre-trained language models. So these models, because they don't need any supervised label data, so with access to a large corpus of text, you could train them in a self-supervised manner. So what we mean by self-supervised manner here is for example, if we take the BERT model, what the authors have done there is they could mask certain words in a text and let the model learn what the masked word is. So this is like one approach that could be used to train your pre-trained language models. And uh, most of the models are either based on the encoder part of the architecture, such as the BERT model. So once trained, these are really helpful for several downstream tasks. So if we do want to fine tune these models, you might not require a large amount of label data. And the other one would be models that are trained on the decoder part, such as the GPT, where it tries to generate text. In terms of the pre-trained word embedding vectors that we've looked, one of the major drawbacks there in comparison to word embeddings produced by these pre-trained language models, such as BERT, is the lack of contextual meaning. So for example, if we take the sentence, I went to the river bank, and I went to the bank to get some money. So what happens with these pre-trained word embeddings is the word bank would be represented by the same vector representation. So this is where these language models and could produce contextualized word embeddings, which depends on the context in which they occur. But while these are able to produce good contextual word embeddings, it doesn't mean that these are good representations of sentences. So there's been quite a lot of research that's been happening where different sentence embedding approaches have been proposed. And today I'm just going to be talking about one of them, which is the sentence transformer model here. So the idea here is it is a modified version of BERT, and the aim here is trying to capture the whole context of a sentence so that it could produce more nuanced embeddings. And so what the authors have done here is what they found was, although models like BERT could produce good embeddings, you also have like the overhead cost. And the other one is they might be, as I said before, they might be good at capturing the word embeddings, but they are not good at capturing it on a sentence level. So what they've done here is they've tried to build a Siamese and triplet network. So basically, the idea here is, are we able to bring sentences closer together that are similar and sentences that are contrastive to be apart? And by doing this, they kind of try to learn the embeddings of these sentences. And currently, there are more than 5,000 pre-trained sentence transformer models available on Hugging Face, which kind of shows the popularity and practical usage of these models, especially for various downstream tasks. And yeah. So this is basically to kind of show you like, depending on the task that you would want to train, you could structure your data set differently. You could kind of use different loss functions. So this library is kind of quite useful. And especially when you don't have like a very huge amount of label data for your downstream tasks. And these are just some examples to kind of show you like where these sentence transformer embeddings are useful. So let's say we would want to kind of understand the semantic similarity between sentences, or even like between an image embedding and a text embedding. Or let's say we would want to do some kind of topic modeling where we want to identify topics that are similar. So these are some of the example downstream tasks where these sentence transformers are really helpful. Right. So where we could see another benefit of using these sentence transformers would be in particular for few short text classification approach. So let's say in practice, getting access to a large amount of annotated data is a challenging process, and especially if we are working in a very resource constrained setting. So this is where few short learning could help a lot. So what we mean by few shot learning is the ability of a model to learn from very few examples. And while we also know that these very recently large language models like ChatGPT, for example, are known to perform well in a few short setting. Let's say you give it a few examples as a prompt, it would do much better. However, there is also this bottleneck, like if we have very limited computational resource, or we don't have access to any cloud capabilities, then this is where something like a few short learning would really be helpful. And setfit is a framework, so this was introduced to address these kind of issues. So what the authors here they've done is, by just providing few examples as possible, they try to make use of the rich text embeddings produced by fine-tuning sentence transformers. So they do this in a contrastive Siamese manner. So what they do here is, based on the examples or the training data that we provide, they try to bring in similar sentences closer and dissimilar sentences apart. And these are then used to train, not training, like a fine tuning the pre-trained sentence transformer models. And these, the representations are then fed into a classification head for classifying the input text. And just to show you the advantage of this approach. Right? So if you can see the graph here, just kind of shows you that with very few examples, a model like a model trained using the set fit framework or approach can actually perform much better in comparison with larger models. And practically at Gosh Drive, this is an approach which we've seen having a lot of practical benefits for a number of use cases, because one of the major bottleneck for us is to getting data annotated. And the other one is because we don't have access to huge computational resources like GPUs. This kind of an approach is, has shown like more practical benefits for us. Right. So now coming on to the next topic, which is large language models. So large language. So what are these large language models? So these are like general purpose models, and unlike models like the pre-trained language models that we've seen, like BERT, these are trained on like really large amount of data using extensive computational resources, and because they are not trained only for a very specific task, they do exhibit a lot of emergent abilities that are not otherwise present in these smaller models. And some of the key advantages that I would like to discuss about these LLMs is, the first one is very recently the open source research community, they have moved their focus towards building these lightweight, small open source LLMs that are actually performing quite well in par with the state of the art closed LLMs like ChatGPT. So as you can see on the graph here, so this is from Microsoft's blog at the time when they released 5.3 model. And now they have this newly released 5.4 model as well. So these are like kind of like excellent examples that shows how the focus is now to scale down the model, but also ensure that the quality of the performance is not compromised. And the next advantage I would say is the LLM generated summaries are actually getting much better than human generated summaries. So this kind of has a lot of scope for a lot of practical tasks. And I would say one main key advantage of these LLMs is their ability to perform zero shot prediction, or in fact a few shot prediction. So what does this mean is we do not have to worry about fine tuning these models, and we could use them straight away out of the box. In the next slide, I will just talk about, like some examples where smaller language models, how their capabilities are used in practice. So one example is the Anthropic team. They've introduced something termed as the contextual retrieval for their Claude model. So for the basic idea here is, for their retrieval augmented generation solution, which is nothing but you would want to retrieve the right amount of information from, let's say, several documents, and then use it to generate the right um, information as outcome. So the core idea behind these RAG solutions is to try to make the retriever better. So what they've come up with is something called contextual retrieval. So basically what they're saying is, in a real world, practically, when we have very limited computational resource, usually what happens is, when you want to retrieve some information, let's say from a 100-page document, you would divide the document into chunks. So when you do that, the context of the chunk gets lost. And the idea here is, what they've said is, in order to make the retriever perform much better, uh, you should you not you should you can kind of add a context about the document chunk that kind of boosts the performance. But how do we do this in a feasible manner? Like, we can't be doing this manually, right? So this is where like LLMs, especially like even the smaller language models, are able to provide an automated way of generating the context about a chunk. The next example is in terms of how research has focused on, is trying to build these really huge large language models and making it perform on several tasks. But what this recent paper have proposed is, rather than trying to train one large language model, you could train several, or you could even fine tune several smaller language models for a particular purpose. So here, what they've proposed is, you could have one the small language model and fine tune it. Like if you see in the diagram, they fine tune the same model to be a planner and then to summarize. And so they kind of also showcase that this can perform much better than closed LLMs. The one last capabilities that I would like to talk about is in terms of annotation or any annotation task where we have to do it in a very resource constrained setting. LLMs could behave like a verification, like it could act as an annotator in the loop, as some sort of like a verifier in terms of human annotation tasks. So that's kind of like one additional advantage of using these SLMs or LLMs. Right. The next one is I'll just talk about how NLP is utilized in practice in industry. So definitely, I would say with the rapid progression in generative AI, we can say that there has been a rise in adoption of AI in general. But however, there's still lots of barriers when it comes to a full adoption of AI. So in particular, there's still the need for better infrastructure and MLOps solutions. So if we take like the healthcare sector, where there's a lot of governance and privacy and ethical concerns, and we would want to build within an on-premise infrastructure. So there's a little bit more challenges comparatively than completely adopting to cloud. And what I found particularly interesting was a few years back, the McKinsey's State of AI report. They did a survey which kind of showed that while people are happy to use computer vision or even natural language text understanding, uh, there's still the lack of use of trying to adopt transformers for building solutions. So I still think that this could be probably because there isn't much more tools for adopting these AI model development. And there's also a recent study conducted by the HIMSS and Medscape that looked into how AI adoption is within the healthcare sector. And they've shown that much of the adoption until now has been focused on administrative tasks. And while we do know that there's still much more scope, much more benefits towards using AI, there are still these gaps that needs to be looked into. Right. So this slide, what I wanted to actually show was this is something that wasn't there when I was doing my PhD, I would say, is in terms of academic research, there's definitely a growing interest towards bridging this gap between the theoretical research and how do we bring things into practice within the industry. So I'm seeing a lot of these academic conferences now are providing a platform for research practitioners within the industry to contribute to the research community by sharing their practical applications, challenges, learnings, by deploying these NLP solutions in a real world setting. So this is kind of like a very encouraging thing. Right. So now, in terms of how we are using NLP in practice within our trust is in terms of building the NLP solutions for our trust. So we are now focusing on a number of use cases, like where we work on different unstructured text information present in clinical reports, such as radiology and genomics. We also work on general purpose text, like patient feedback comments. And right now, most of our pipelines that are being built are focused on extracting pertinent structured information. And this could involve like tasks such as semantic search, topic modeling, named entity recognition, question answering, and so on. And depending on other use cases, we are also looking into sentiment analysis, text classification approaches. And in terms of future work, we are also now looking into retrieval augmented generation. What is the best way of providing outcomes to clinicians and staffs? Right. So why are we now focusing on, particularly focusing on unstructured data is, so when we spoke with some of our clinicians, what we found was, in reality, much of the information that is being digitally stored within our electronic patient record systems is in the form of unstructured text. So this could be in different formats, such as text, like discharge summaries, test reports. And what we also found was these contain valuable information that is not currently present anywhere within the available structured information. So by providing an automated solution where we are able to extract these information from large volumes of unstructured information, this would help in answering a lot of clinical questions in a timely manner, and it could also aid with the clinical decision-making process. So in the next few slides, I'm going to talk about a couple of use cases that we are working now, but this is not really related to the extracting these structured information, but this is more towards how do we help other teams within the trust to improve their manual processing. So this one, so the family and friends test. So this is a tool that is used by the NHS within the UK. So the NHS, which I should have actually talked about before, is the National Health Service, which is a publicly funded healthcare system, and GOSH is a part of the NHS. So what this tool is used for is for collecting patient feedback. So in our trust, this feedback collected is kind of quite unique, because we also get, being a pediatric hospital, we also get the feedback provided by children as well. So this would mean that lots of the feedback might not be grammatically relevant. So it's written by children, right? So while this is very valuable data, it can provide a lot of insightful information to understand about the patient experience and also about the services. But to be able to make it more insightful, it requires a manual and tedious process. So our patient experience team have to manually look through like tons of these comments every day, and they have to tag their sentiment and themes in a way so that it could be used for analysis. And each comment is assigned like a positive and a negative sentiment, and also like a specific theme, like it could be like whether it is a general theme or is it more about comfort or about emotional support. In terms of the project flow, so the main aim of the project from our end was to leverage the capabilities of NLP and make this process more efficient for the patient experience team. So what we did was build a toolkit that could also be easily implemented across trusts. So it is very, very lightweight. It just makes use of CPU capabilities, and it's mainly developed using open source. And we also focused on building modularized pipelines so that it could be kind of reused for other projects within uh, Drive. And some of the key components is like trying to normalize the text, trying to remove special characters, making it a little bit more also balanced based on the themes and sentiment. And also like the main aim was trying to train our own models with our in-house data and to kind of gather the performance metrics, and also to analyze like how does it work on unseen data, could it be useful for other data within the trust. And the main component would be to ensure that we do have like a smooth deployment and it runs. So this this pipeline actually runs every day within our on-premise infrastructure. Just to give you an overview of how the data looks like. So in terms of sentiment and themes, so this is based on the data that has been manually annotated by our patient experience team. And as you can see here, this is real world data, very highly imbalanced. And if we think about it from the trust's point of view, we do want to get more reviews, like more positive reviews. However, in terms of machine learning approach, this data is heavily skewed. So how did we tackle this problem? How did we approach a solution? So what we did is, as I mentioned earlier, we make use of the set fit approach by using a fine-tuned sentence transformer model that we trained on our in-house data. And then we kind of use the annotated labels for both the sentiment and theme classification. And here I'm showing some examples to kind of show you um, the potential benefit of using the representations from these fine-tuned sentence transformer models. So we also kind of interpreted them using a model explainability tool. So here, if you look at the attribute label and the attributes, so for this sentence, the staff were incredibly caring, but the wait time was too long. We can kind of see which words kind of attributed to the negative sentiment. So this kind of also shows like where models like the approaches like sentence transformers and could actually help us. And just to talk about the result is so we did start with a simpler approach like by training a classical SPM model just using bag of words, but that kind of provided only 40% accuracy for both the sentiment and theme classification. But in terms of once we fine tuned the sentence transformer and then used the set fit approach, it kind of boosted the performance. There's still room for improvement for theme classification, but again, because this is a very subjective topic, there's a lot of overlap, especially with the themes, which could actually depend on the annotator who's annotating the data as well. So in terms of the overall approach, what I would say is this is more lightweight, and it is able to utilize only CPU capabilities for training the models. The next use case I would like to talk about is the work that we did or are doing with our quality improvement team. So what we are doing here is processing and classifying radiology reports. So radiology reports, as we know, it contains a lot of clinical terms, medical terms that are often complex to understand. So it definitely requires a clinical expert when we do want to annotate these reports. So what the quality improvement team are doing is they are working on a project that focuses on identifying any preventable fracture happening within the hospital. And they have been looking into a lot of outcome measures and on how do they reduce the risk, and how could they prevent the fracture from happening. And one of the measures was to identify such information from these radiology reports. So this is where we kind of help them by developing a model and a pipeline to process these reports, because having to go over these reports manually would mean that they need a dedicated time of clinicians. So our objectives was to build an end-to-end pipeline that can detect these radiology reports, which needs a further investigation of pathology fractures. And in this end-to-end pipeline, what we've done is we've made use of an LLM to summarize the report with respect to any mention of pathological fracture. And by doing so, we would wanted to also kind of understand the impact of summarizing the report rather than using them directly. Also to understand the challenges around using such LLM-based solution. And mainly this was, again, as I said before, our on-premise infrastructure does not have high compute capabilities like GPUs. So this is kind of designed for very low compute environments that can run on CPUs. And so in terms of the overall architecture, so we have like two stages where in the training and validation stage, this would involve having the clinician in the loop, having expert annotators, training models, and the final models are moved into deployment, having finalized with the clinician. And the key idea behind, as I said before, for this pipeline is to use the LLM summarizer to summarize the reports. And uh, what advantages I would say we had by summarizing the reports rather than using them directly was it kind of normalizes the reports written by different clinicians so that the model is not biased towards a particular way of the way the language is expressed. And two, by summarizing the information only relevant to pathological fractures, it kind of removes any other non-relevant information present in the report. There were three different experiments that we tried. So the first one, as I said before, was just straight away use the radiology reports, the expert annotated labels. And again, here we use the set fit approach. And even though the model was trained based on expert annotated data, it failed to understand the complex meaning of the medical or clinical terms present. So it kind of achieved only 52% accuracy. And in terms of the summarization, we still used a small language model to get a summarized version of the radiology report. And once we used the summarized text to train the model, we found the accuracy to have improved to 75%. And then later we started to use some data balancing strategies like oversampling, because as we all know, not every report needs to be positive about having a pathological fractures, right? So it was very highly skewed. So let's say out of 100 reports, probably you might find 2 or 3 reports that talks about pathological fractures. So by oversampling the data, it kind of helped boost the performance to 92%. And in general, what I would say is any use case that we work, especially within the healthcare sector, is to ensure that we don't miss any positive cases, even if negative cases are predicted wrongly. I wouldn't say it's fine, but it is quite important to ensure that we don't miss any of the positive cases. So that's something that we are always focusing on, and also to ensure that at every stage we would have the clinician in the loop to validate the pipeline and the AI model. Right. So in terms of our learnings, very specific to the language, the large language models, I would say is because we now have access to tons of these models, like lots of progress happening within the open source community itself. It is not like a necessity that we would need to use them. So start simple, like not every problem might require an LLM pipeline. In fact, what I've seen is in most use cases, just using some simple rules, you would be able to solve the problem. And small language models are now becoming practically effective, even as a zero shot and few shot learning. And they're quite good for downstream applications. And where practically I would say this is quite useful is when you do have like higher CPU compute. This is you could start using them practically. And in terms of, we did a few other work where it kind of focused on like using quantized model, that's trying to shrink these larger models to be able to use on a CPU inference. But what we've seen is it is still not a feasible solution. Like investing in GPUs would definitely solve these issues. And I guess that's all. Like, thank you so much, everyone. Like, thanks for listening. I hope you found it useful.
Thank you, madam. And if anyone's having questions, you can just unmute and ask. or else you can just put the questions in the chat also.
So I have a small question. The thing is like, are you all like directly getting the input as text, or is it like from images? When you told like you get feedback from children as well, right? So do you get it like digitally itself as text, or is it like you take in a piece of paper and then you all take a picture and convert it to a text using OCR?
So that's a good question. So what happens is we do have like two approaches. One, digitally, you could fill in the form, and you could also have it on a paper. So you would have like comments like what went well, like what was good, what was bad, and at the moment, so this information gets collected into the database by the patient experience team. So we have access to that database rather than the step before.
Okay, so if it's like digitally itself, if you take it from a form, that's all
Yeah, then
right.
you could access it through the database.
Yeah, if it's like an image and if you all are using like OCR and if it's a children's handwriting, isn't it
It's
hard to
gonna be, yeah,
detect?
that's like another AI project, right? Like using computer vision. Yep.
Thank you.
There's a question in the chat, Madam, as any possibilities to use robotic process automation document understanding capabilities?
So the challenge here is, although like I haven't talked about the data engineering process, it is very complex. So even though it is digitally present, like it's I would say it is a very, very complex piece. Like even to let's say for example, we would want to retrieve radiology reports. It would be present in different electronic patient record systems. So some of it might be present in one system, some of it in another. It might not have any metadata. So trying to even gather that is it is a complex task. It's not like very straightforward.
Okay, madam, and there's another more question that was raised during the registration as how to fine-tune or rack results and whether it provide good results.
Sorry, like fine tuning.
Yeah, how to fine-tune or rack results and whether it provides good results. That's
You
how
mean for
it's mentioned.
rack solutions, is it?
Yeah, I guess, madam.
So in terms of I'm sure fine tuning would how to fine tune or rack result, whether it provides a good result. I would say definitely fine tuning would provide good result, especially if you take our data. It is quite unique. One being it pediatric data, and two because our hospital like they care for children with rare and complex disease. Every data is quite unique. So by fine tuning, definitely it will provide good result. But again, it depends on your use case. Let's say you would want to maybe use models on like some generic data. You might actually find that like off the shelf, the model should give you a good baseline. How do you evaluate fine-tuned LLM models, any performance? It is a tricky one because it also depends on the use case. So depending on the use case, depending on what the success criteria would be, it would be based on interacting with the clinicians, with the staff. So for example, if you take the family and friends test, if the team comes to us and says like, we don't mind if it misses any negative reviews. This is just an example I'm giving, but we would want to make sure that we want to pick all the positive ones. Or if they say right 80%, if the model is able to do well and it is missing 20%, we are still fine to manually look into them. Then, so it kind of depends not only on the machine learning performance metric, so it kind of depends on the use case and, like the stakeholder as well. But at the moment, in terms of the fine-tuned LLMs, because we don't use them as a generative task, we've been using them more towards utilizing them for a downstream task. So we use metrics like a F1 score, precision, and recall.
Hello, thank you for the nice presentation. This is Sarvis. So your data, I mean, specifically this sentiment data, are all in like English language, or do you also deal with other languages?
No, at the moment it's English.
Okay, so we are interested, like at least myself and few like people here are interested, and we are also like developing resources for the Tamil language, Tamil and Sinhala languages. So,
Yep.
And so for us, small language models would be interesting, although I mean we are not sure how much they are capable of handling our languages. Have you come across any like small like language models which are developed specifically for low resource settings, or maybe South Asian?
Yes, there's quite a lot happening. Although I'm not actively involved, I have seen that there is a lot of research going on these low resource setting, especially maybe I can, after the call, I can send you a few research groups and research people's name who are actively working on it.
Yeah, that would be great.
Yeah,
Thank
yeah.
you.
It seems like end of the questions, and thank you for the answers, madam. And good evening. On behalf of the IEEE Women in Engineering Student Branch Affinity Group of the University of Jaffna, I would like to express our heartfelt gratitude to our esteemed speaker, Dr. Pavithra Rajendran, for sharing her insights with us today. Dear Madam, your comprehensive exploration of NLP pipelines for pediatric healthcare, including techniques for processing clinical texts and unlocking valuable insights, has truly enriched our understanding and inspired new avenues for research and innovation. We deeply appreciate the time, effort, and expertise you generously share with us today. Madam, please accept this virtual token of appreciation we have prepared as a small gesture of our gratitude. I would also like to extend a warm thank you to all the participants who took the time to join us tonight. And as we come to the end of today's session, it's perfectly okay if you are unable to switch on your cameras, but we kindly request everyone to join us for a group photo, and it would be wonderful to capture this moment together. Thank you once again, and have a wonderful evening.
Thank you all. Thanks for inviting me again. Like all the very best for your career. Yeah.
Thank you so much.